Okay, in yesterday's class, we started talking about, we talked about how the time response of first order system looks like, how the, like, if a first order system is excited, or the input to the first order system, if it is like different types of standard signals like impulse, ramp, step, parabolic, then how the output of the system uh, responds. So then we started we started our discussion on what will happen if you are given with a second order system. So in case of a second order system, so this we had already talked that in case of a second order system, basically there are a few parameters which affect the overall response of the system. So for each type of input which is provided to the second order system, suppose we are providing a step input to the second order system. So corresponding to that step input, there can be 4 different types of cases which may arise in a second order system. So that 4 different types of cases are, they depend on the value of what is known as damping ratio, that is zeta. So depending on the value of zeta, whether zeta is equals to 0, 1, less than 1, more than 1, depending on the value of zeta, you will have different types of system. Different types of system in the sense the response of the system, they will vary. So if the value of your damping ratio is 0, so that means there is no damping in the system, and the system will behave as an undamped, or it will be known as an undamped system. If the value of zeta, it lies between 0 and 1, then we say that the system is an underdamped system. If the value of zeta is equals to 1, then it is a critically damped system, and when the value of zeta is greater than 1, then it is an overdamped system. So now let's see like how, what does it mean by overdamped, underdamped, critically damped, these kind of things. So let us take an example of, let's say, a simple pendulum. Okay, so in a pendulum, let's say you have, so this is, let us say this is your pendulum. Okay, so this is your steady state position where the value of theta is equals to 0 degree. Now what we do is that let us assume that we give some initial condition, and now the pendulum is somewhere over here, and now this is the value of theta. So the theta is equals to, let us say, 15 degree. Okay, so we move this pendulum from its equilibrium position, we take it to a position where theta is equals to 15 degree, and from there we release the pendulum. So what will happen? The pendulum will start to oscillate. So it will start oscillating like this, then it will again go back, and then it will keep on oscillating. So the oscillation of this pendulum, that depends on the external factors, or external factors as in what is the damping which is there in the system. Okay, so if let us say that if there is no, let's say that it's in a there is no friction in air, or there are any kind of friction or any kind of damping is not present in the system. So if that is the case, then what will happen is that this pendulum, it will keep on oscillating. It will start from theta equals to plus 15 degree, it will move all the way to theta equals to minus 15 degree, again go back. So that means a sustained oscillation. So in case of no, so case number 1 can be if there are no friction or damping. So that means the pendulum will keep on oscillating for infinite time. So that means it will have sustained oscillations. And that response is given by this undamped response. So you see, in case of an undamped response, you have a purely sinusoidal oscillation, and this sinusoidal oscillation, the magnitude or the amplitude of this sinusoidal oscillation, it remains same throughout time. It is not getting reduced with time. So it will have sustained oscillation with same amplitude. Okay, then let us say that you have another case where you have some amount of friction is present in the air. Okay, so in this case number 2, some some friction is present. Okay, so if some friction is present, so that means what will happen is that that friction or that effect of the of that friction on the pendulum, what it will do is that it will keep on restricting, or it will keep on opposing the oscillation of this pendulum. So that means what the pendulum will do is that it will start from plus 15 degree on the right. It will come it might not reach minus 15 degree to the left. It might go to, let's say, minus 14.5 degree to the right. Then again while going to the left, then again while going to the right, it will not reach 15 degree, it will, let's say, it goes to 14 degree, and so on and so forth. It will keep on oscillating until and unless it comes back to its original or the equilibrium state. So this kind of an situation where your oscillations are, so that means the oscillations are dying down with time. Given a sufficiently large amount of time, this oscillation will keep on reducing and the system and the pendulum will come back to its equilibrium position. So that kind of a system is known as a underdamped system. So this, in case there is some friction, so you will have decaying oscillations. That means the amplitude of the oscillations will be reducing will get reduced over time, and this is known as an underdamped system where the value of zeta is less than 1. So here no damping means the value of zeta was equals to 0. So if there is some friction, then the value of zeta will lie somewhere between 0 and 1. It will lie between somewhere 0 and 1. Now let's say you have another case where you have a significant amount of friction or a significant amount of restricting force, and what that restricting force is doing is that you start from here and it comes and stops just over at theta equals to 0. Okay, so that means that in the third case, let's say the pendulum starts at plus 15 degree and slowly comes to a stop at theta equals to 0 degree. So that means it is not going to the left hand side. So that means there are no oscillations as such. It is directly coming from 15 degree. It is taking some time and it is settling, or it is stopping at the position theta equals to 0. So, and let us say that the time which is taken by this pendulum to reach from theta equals to 15 to theta equals to 0, that is, let's say, time t equals to, let us say, 5 seconds. Okay, so in this kind of a situation where you have a sufficient amount of damping in the system such that the oscillation, no longer any oscillations are present in the system, those kind of systems are known as strongly damped or over damped system. So this is an overdamped system where the value of zeta is greater than 1. Okay, so in case of an overdamped system, you do not have any kind of oscillation. You will just the output will just slowly decay and it will reach the steady state value. Now, and critically damped is basically a category of, or you can say that it's a category of overdamped system. So the difference between so the definition of critically damped is that if, let us say, that the time taken by this pendulum to reach here, in one case it's 5 seconds, and the minimum time at which the pendulum takes to reach here, if that is, let's say, 1 second, then that condition is known as the critically damped condition. So in case of a critically damped, what will happen is that similar kind of the response will be followed. That is, the pendulum will start from plus 15 degree and reach to theta equals to 0 degree, stop at the equilibrium position, and the time taken for this action, that will be the minimum amount of time. If that is the case, then it is known as the critically damped, and for this critically damped, the value of zeta is equals to 1. Okay, so now let's see that if you have a second order if you are given with a second order closed loop system. So in that case, so we have seen that the general expression for a second order system is basically Cs by Rs is equals to omega n square by s square plus 2 zeta omega n s plus omega n square. So this is the general transfer function of a unity feedback second order system. Okay, so now what we want or what we want to verify is that if we are providing some, let's say some different kinds of standard signals like this step, impulse and all, then we want to see how the system is responding to those kind of inputs. So why do we, just to recap, why do we need these kind of, why do we need to study the response of any kind of system to a fixed set of standard systems? So this need basically comes from the design point of view. So whenever you have been given, you have a plant and you want to control, you want to design a controller so that the overall plant will give you a desired output. So while designing, you will be given a fixed set of criteria and you have to see how your system is responding to various different kinds of input, because at the end of the day you actually do not know what will be the exact input which will be provided to your system. So you have to design your system, you have to set the parameters of your system in such a way so that you can say that fine, that my system is performing satisfactorily to like impulse, step, ramp and parabolic. So given these conditions, we are expecting that if we have a different kind of input, then the system will also perform in the desired manner. Okay, so that is why we need to study the response or the time response of any given system for a set of standard test signals. So similarly here, let's take the case of an unit impulse. So unit impulse means the value of Rs is going to be 1. So you can write Cs will be equals to nothing but omega n square by s square plus 2 zeta omega n s plus omega n square. Now, as we have said that for each kind of input, we can study 4 different cases. So let's take the first case where the value of zeta is equals to 0. So that means the system is an undamped system. So undamped system means Cs will be given, so value of zeta will be 0. So Cs will be omega n square by a square plus omega n square. Now if you do the Laplace inverse of this, you will get the value of Ct, which you see that the expression of Ct, it has a sinusoidal term over here. So that means there is only a sinusoidal term and there is no so that means that the signal will be a purely oscillatory signal and will keep on oscillating without any change in its amplitude. If you want to see what is the transient, so in this case actually the steady, you see that there is the transients do not die down with time. So there is no amount, so this value of sine omega n t, that is not equals to 0 while t tends to infinity. So that means that the system will not reach a steady state as such, and the system will have a continued or a sustained oscillation throughout time. Now if we consider some amount of damping, let's say we consider an underdamped system where the value of zeta is less than 1. So in case the value of zeta is less than 1, what you can do is that you can simplify or you can factorize the denominator into 2 terms like zeta omega n plus s plus zeta omega n minus j omega d multiplied by s plus zeta omega n plus j omega d. So and this omega d is basically we have learned earlier that omega d is known as the damped frequency. And it depends on the undamped natural frequency and the value of the damping coefficient. So if you take the Laplace inverse of of this term, you will end up with a equation like this, wherein you can see that the value of the overall time response is given by omega n by square root of 1 minus zeta square e to the power minus zeta omega n t multiplied by sine omega t into t. So here you see that there is an exponential, a negative exponential term present in this overall system response. So that means that because of this negative exponential, so that means this negative exponential will tend to 0 as, so this negative exponential e to the power minus zeta omega in t will tend to 0 as your t tends to infinity, right? So that means at steady state, this value of Ct will be equals to 0. So the steady state value of this output will be equals to 0, and the transient output will be given by this whole function. And now here, since there is a sinusoidal term attached, sinusoidal term associated with this output, so that means there will be some oscillation, but the oscillation will slowly decay down with respect to this decay down following an exponential response. Okay, so that means this sine omega dt, this term will correspond to some oscillations in the system, and this omega in e to the power zeta omega e to the power minus zeta omega in t, this will result in a damping or reducing the oscillations with time. So CSS is equal to 0, right? So because of these two terms which are present in the system, you will see that there will be some oscillations, and the oscillations will slowly die down according to the damping ratio and according to the value of this exponent. Now, if you have a critically damped system, okay, so in case of a critically damped system, the value of zeta is equals to 1. So then the Laplace, the time response is given by an equation which looks like this. So in critically damped system, what will happen is that there will, since there is no sine or cos term present in this system, so that's there won't be any oscillations, but there might be a peak, and after that peak, it again comes back to its steady state. So the steady state over here is equals to CSS is again equals to 0, because this e to the power minus omega in t, this term is going to e to the power minus omega in t. This is going to 0 as t tends to infinity. So that means this is the transient response, and the steady state response is equals to 0. So in case of a critically damped system, if you have if you are providing an impulse response, if you are providing an impulse input to the second order system, you will have a peak, and then after that peak, the system will slowly come down to go down to its steady state value. So there won't be any oscillations which we saw in the previous case when we were dealing with the underdamped system. Similarly, if you consider the overdamped system, again a similar kind of damping will be present, but the response will be similar to the critically damped case, but just the difference would be the time taken for this system to reach the steady state will be more compared to the time taken by the critically damped system. So if you see here, the critically damped system, let's say it is going to steady state at this point. So at t equals to 2 seconds, the system is going to steady state, let us say. But here you see that it is taking, so maybe probably at somewhere over here, let's say t equals to some 3.5 seconds, it is going to the steady state. So that means the only difference between the overdamped and the critically damped system is that the time taken by the system to reach the steady state, that is minimum in case of a critically damped system, and it will be more in case of an overdamped system. And also there will be some effect on the peak overshoot also. So the peak overshoot means the amplitude or the magnitude of this maximum peak that we are getting. So this peak is also the amplitude of this peak is also affected, or that is also different when we are dealing with the critically damped system or an over damped system. Okay, so now similarly let us see if the time response of the second order system when we have a step input. So in case of a step input, similarly if you for this undamped system, that is zeta equals to 0, the output is given by 1 minus cos omega n t. Okay, so from this equation you can see that there is this cos term, so that means there will be sustained oscillations in the system in absence of any damping. Okay, and this system the amplitude of the sustained oscillation with constant amplitude. In the system, and then so that means that the transients only continue throughout the time and the system never really reaches a steady state. Similarly, if you see for an underdamped system, so in an underdamped system you will again have to do the Laplace inverse. You have to separate out the Laplace transform into partial fractions, and then you can, if you do the Laplace inverse, you will see that the value of Ct is given by 1 minus e to the power minus zeta omega n t divided by root over 1 minus zeta square, and there is some term sine omega dt plus theta. Okay, so here you see that again you have this sine term, so that means there will be some oscillations, and you have this e to the power minus zeta omega n t terms, so that means it will act as some kind of damping, or it will the effect of this negative exponential will reduce the amplitude of the oscillations. So here you see that the response goes like it will start oscillating, and slowly the oscillations will die down and the amplitude of the oscillations will reduce, and slowly it will reach the steady state. Now if you want to see the transient part of this overall time response, so this transient part, so see TR of T will be equals to this the term related to this negative exponential, because this is the term which is going to 0 at t equals to infinity. So e to the power minus zeta omega n t by square root of 1 minus zeta square sine omega dt plus theta. So this is the transient part of my response, and the steady state part of the response is when this is equals to 0. So that means the steady state value will be equals to 1. So here you see that the response is starting from 0. It is going through some oscillations, and finally it is settling down to a value which is equals to 1. Now, an interesting thing to observe over here is that this oscillation, or this damped oscillations, that is basically, it's basically following, so there is this, so you can say that it is actually, there are like two envelopes like this, and the sinusoidal signal is basically following, or it is enclosed by these two envelopes. So these two envelopes, so this first one is given by 1 plus e to the power minus zeta omega n t divided by 1 minus zeta square, and the bottom one is given by so that means that the oscillation or the decaying oscillation is basically enclosed by two envelopes, and the term of these envelopes are given by one. So one term is given by e to the power given by 1 minus e to the power minus zeta omega n t, and the other one is given by 1 plus e to the power minus zeta omega n t by square root of 1 minus zeta square. Now for a critically damped case, so obviously for a critically damped case, there won't be any oscillations as the name suggests, and similarly that can be proved from the overall time response also. Here you see that the overall time response, there are two exponential components, or you can write that the transient part of this response is equals to this part, which is equals to, if you take this will be 1 plus omega n t e to the power minus omega n into t. So this is your transient part, and your steady state part will be equals to this part will, these two terms will go to 0. So the steady state response will be equals to 1. So the system will start from 0. It will no longer have any peaks or any kind of oscillations. It will straight away, it will follow an exponential curve and it will reach its steady state value, which is equals to 1. And for an overdamped case where the value of zeta is greater than 1, similar kind of response will be followed. It's just that the time taken by the response to reach the final value or the steady state value, that is more in case of an overdamped system. So this is the general expression for this the time response of an overdamped system when it is excited or when the input to the system is a step response, is a unit step input. So here also similarly you can see that both this second term and the third term, they have this e to the power minus, have negative exponentials attached to it. So that means these two terms will go down to 0 or will die down to 0 as the time t tends to infinity, and the steady state value will be equals to 1. So here also the steady state value is equals to 1, and the other two terms they will comprise of the transient response of the system. Okay. So now if you sort of combine everything together just to visualize how things are changing. So this will be the case when, so let's say you have a system and you are providing a unit step input to that system, to that second order system. So if the value of zeta is equals to 0, then you will have sustained oscillation, which is given by this blue curve. When the value of zeta lies between 0 and 1, so then you will have some oscillations. So this green and this red curve, they basically, you will have some oscillations and slowly it will go down to 0. If the more the value of zeta, the lesser will be the amplitude of the peak overshoot. Okay, so here you see that in this case the value of zeta was equal to 4, and in this red curve the value of zeta is equals to 0.5. So that means the value of zeta is increasing, that is the damping, that is damping in the system, that is more. So more the damping, as the like common sense, you can say from common sense that if the damping is more, so that means first of all the system will reach the steady state earlier, and also the maximum or the value of that peak overshoot that we are getting, the value of this peak oscillation, that will be less when the damping is more. When you have the critically damped system, so this oscillations no longer, you won't find a peak as such, you will directly, so it will be directly an exponential curve and it will reach to the steady state. And in case of an overdamped system, so that again in case of an overdamped system, there won't be any kind of oscillation and it will directly go to the steady state, but it will take a longer time to reach the steady state condition. Okay, so this time response thing is clear to you?
Yes, ma'am.
Okay, so this derivations of this, if you can try to solve or the mostly it's given over here, but the derivation of these Laplace inverse and how you are getting the value of CT by doing the Laplace inverse of the corresponding CS value, that you can try at home, and you will see that you will get an equation which is given by this CT value. So now you see that, so now let's say that so whenever you are given with a second order system, or not only a second order system, it can be in any order of system. So if the response, let's say the system response is given by Cs equals to omega n square by s square plus 2 zeta omega n s plus omega n square, right? So in case you have been given with a system like this, so we can say that the characteristic equation, so by definition, characteristic equation is defined as the denominator polynomial of that system. If we equate the denominator polynomial of a system to 0, that is known as the characteristic equation of that corresponding system. So here the characteristic equation, so it is generally denoted by delta. So the value of delta is equals to s square plus 2 zeta omega n s plus omega n square will be equal to 0. Okay, so now if you find the roots of, if you solve this characteristic equation, and if you find the roots of this characteristic equation, so you can say that these roots, they are nothing but the poles of the system, because poles of the system also means that you have to find the roots of the denominator polynomial, and the denominator polynomial is nothing but the characteristic equation. So that means if you find the roots of this characteristic equation, it will be given by s. So there will, it is a second order system, second order equation. So that means there will be two roots in the system. So one will be s1 and another is s2. So then this value of s1 and s2 is given by minus zeta omega n plus minus j omega n square root of 1 minus zeta square. Okay, so this is so now, so let us write this as minus alpha plus minus j omega, right? So the value of sorry, so the value of alpha is equals to zeta omega n, and the value of omega will be equals to omega n square root of 1 minus zeta square, or you can say that omega is equal to omega d, which is the damped frequency of oscillation. And alpha is basically known as, so this value zeta omega n, this is known as the damping constant, and omega n is the undamped natural frequency of the system. And if you plot this, so in this S-plane, so S-plane means a plot for on the, so the value of S is equals to zeta sigma plus j omega. So if you plot the value of s in this S-plane, so the real part of this s is in the x-axis, and the imaginary part of the value of x is given in the y-axis. So here you see that you have minus alpha plus minus j omega. Okay, so now let us say that, or rather if we want to find plot this one, so this value will be equals to minus zeta omega n, and this the real part is equals to minus zeta omega n, and the imaginary part of this pole is equals to omega n square root of 1 minus zeta square. And there are like two, so these poles are a pair of, so it is a pair of complex conjugate poles. So that means one root will be at S1 at this position, and the other root will be at a position like this. And if you find the value of, so if you see that this angle which this omega, this vector or this line makes, if you draw a line from connecting this this pole S1 to the origin, so the angle this line makes with the real axis, that is given by the value of theta, and theta is nothing but cos inverse of zeta. Okay, and so this is the value of, this is theta, and omega n is basically the radial distance between the roots to the origin of the S-plane. Similarly, so this one is also, this value is also omega n, and this angle is also theta, because these two are a pair of complex conjugate poles. So that means the values are same. It's just that the imaginary part is, the real part is same, the imaginary part has a negative value. So that means the omega n, you can say that in an S-plane, omega n is defined as the radial distance from the roots to the origin of the S-plane. And alpha is obviously the real part of the roots, and omega is known as the conditional frequency, and it corresponds to the imaginary part of the roots. Now, why do we need to see like what are the position of the poles in that S-plane? So how does it matter to us? The significance comes from the point that if the pole of your system, if the poles they lie on the left hand side of the S-plane, that means that there is a positive damping in your system. So if it lies in the left hand side of the S-plane, so that means there is positive damping. If your poles they lie on the right hand side of the S-plane, so that signifies that there is negative damping. And if the poles they lie on the imaginary axis, that signifies that the value of there is zero damping, so that means the value of zeta will be equals to 0. So on the left hand side means the value of zeta is a positive value, so zeta is greater than 0. Negative damping means the value of zeta is less than 0, and if the poles they lie on the imaginary axis, it signifies that the damping there is zero damping. Now, in case of a positive damping, we have seen that if the value of zeta it lies between 0 and -1, we have seen that the step response it actually settles to a final constant or a final steady state value, and this settling basically occurs because there is an e to the power a negative exponent present in the system response. Because of this negative exponent which is present, there is the step response that slowly decays down to the steady state value. But if you have a negative damping, so negative damping means the value of zeta is less than 0. So the moment the value of zeta is less than 0, so that means in the output you will have a positive exponent, and if there is a positive exponent present in your output, so that means the output will keep on increasing without any bound. So that means the system will move to instability, or it will become unstable if you have a negative damping in your system. And similarly for like zero damping, we have seen that the cases where zeta is equals to 0, we had some sinusoidal term, we had either some sine something term or cos something term. So depending on type of response, so because when the value of zeta is equals to 0, you have this purely sinusoidal terms which are present in the response. So that means that the response to that system will have sustained sinusoidal oscillations if the poles of your system they lie on the imaginary axis. Okay, so here and when the poles they are lying on the imaginary axis, we say that the system is sort of, you can say that the system is marginally stable. So it is neither stable nor unstable, so it is at a margin, so it is known as a marginally stable system. So basically the significance is that the location of the characteristic equation roots, they determine characteristic equation roots that is equivalent to the poles of the system, and this basically determines the time response of the system. So if you have a system and if you can find out what are the poles which are present in the system, you can predict what kind of a response, the nature of the response of the time response of the system. Okay, so here let's see some of the some characteristics or some kind of different response of time responses when the root locations are different in the S-plane. So if you have like two roots with for a second order system, both the roots or both the poles they lie in the left half of the S-plane, so that means the value of zeta is greater than 1. In that case, what you will have is that you will have no oscillations. The response will start from 0, follow an exponential path and slowly go to the steady state. So this is the step. So this is basically the step input which is provided to your system. Now if the system has like the two poles of the system, they lie on the real axis and both the poles they have the same value. So that means there is like repeated poles at, so in this case this is repeat So this is repeated poles or repeated real poles, you can say. Okay, so you have two poles at the same position. In that case, that is also, so that is the criteria, or that is the case when the value of zeta is equals to 1. That means the critically damped system. So critically damped system will also follow a similar exponential path, just that the settling time is minimum for the system. Now, if you have an overdamped and underdamped system, that is the value of zeta lies between 1 and 0. So that means that there will be a pair of complex conjugate poles. So there is one pole over here and the other pole lies over here. So this is S1, this is S2. In this case, you will have some oscillations in your system, but these oscillations will keep on, will slowly die down because of the negative exponent which is present in the time response. Now, if you have if the value of zeta is equals to 0, so that means if the poles they lie on the imaginary axis. So here you see there are two poles which are lying on the imaginary axis, one with some plus j omega value and the other with minus j omega. So if this pole is at, the position of this pole is at plus omega and position of this pole is at minus omega. So in that kind of a situation, you will have a sustained oscillation throughout time. Now, if the value of zeta, if you have a negative damping in your systems, damping in your system means the value of zeta is less than 0, but it lies between 0 and minus 1. That is, you will have a pair of complex conjugate poles lying in the right half of the S-plane. Then that signifies that the output will have oscillations, but these oscillations will keep on increasing with time without any bound. So that means the system will become, so the system here is unstable if you have negative damping, and the negative damping lies between 0 and minus 1. And if the negative damping is such that the poles they lie on the real axis but on the right half of the S-plane, in that case there won't be any oscillations. It will exponentially, the output will exponentially increase to infinity. So in this case also the system becomes unstable. So from this type of responses, you can see that if the pole position or the poles of the second order system or any kind of system, if they lie on the right half side of the S-plane, so that signifies that the system is unstable. If the poles they lie on the left hand side of the S-plane, then the system will be stable, and the system will be said that it's marginally stable if the poles lie on the imaginary axis. Now, we'll see something which is known as a dominant pole. So a pole, basically, you see that when we saw the calculation for the impulse response of a second order system, so that was pretty easy to calculate because the Laplace inverses were not so complicated. When we were talking about, or when we were dealing with the step response of the second order system, in case of the step response, you saw that the calculations became little bit more complicated, right? And the overall calculations for the second order system is more complex or more complicated compared to the first order system. So you can imagine that as the order of your system increases, that means that the step responses becomes much more harder to generalize and to compute. So for those kind of cases, when we are dealing with a higher order system, so what we can do is that we can do some kind of approximation of the system so that we can easily analyze the system and find out what is the response corresponding to that system. So for this kind of approximation of a higher order system to a lower order system, we use something which is known as dominant pole approximation. So what is a dominant pole? So by definition, dominant pole means the pole which is closer to the origin, or the pole which lies closer to the imaginary axis compared to the other poles of the system, that is known as the dominant pole. So if this is your j omega axis and this is your this axis. So if you have a pole, let's say a pole over here, a pole over here, and there is another pole over here. So let's say that in this system you have like 3 poles. So the pole which is lying closest to the origin or closest to the j omega axis, which is this pole. So this is, let's say, S1, S2, S3. So this pole S1, which is closest to this imaginary axis, this is known as the dominant pole, and the dominant pole, and this dominant pole, basically it has the smallest real value. So the value of sigma, smallest value of sigma among all the other poles. Okay, and the other significant property of this dominant pole is that it has the largest time constant. So largest time constant means it is the slowest to respond. So that means this dominant pole, basically, so by definition, it is the pole which is lying closest to the origin. Then it has the highest or the largest time constant. So that means the effect of this pole on the system response, that effect is the slowest or the most slow component of the overall response. And basically this dominant pole, this is significant and it is required while we are analyzing the stability of a system. So later on we'll discuss about how to find out how much stable the system is, or whether the system is at all stable or not. So here we saw that this was a generalized idea of stability, that depending on the position of the poles, whether the system will be stable or unstable. Then in the later on we'll see that depending on the, so now let's say that if your poles are all in the left half plane, so that means the system is stable, but you don't know how stable your system is. So depending on the exact location of these poles, we have to find out the relative stability or the extent up to which the system is stable. So for those cases, this dominant pole, this is mainly important. And also for some approximation, we'll talk.
Ma'am, you're not audible, ma'am.
Hello.
Yes, ma'am, you're audible now, ma'am.
Yeah, no, so actually there has been a power cut here. So I don't know when it will come. So we'll continue this talking about this dominant pole in the next class. And is there any doubt in understanding today's lecture?
No, ma'am.
Okay, fine. And did you go through the solution for the quiz?
Yes, ma'am.
Okay, so things were like clear how the solutions were done or how the problems were solved?
Yes, ma'am.
Okay, fine. So then that's all from my side today. So we'll continue talking about this dominant pole approximation in the next class.
Yes, ma'am. Thank you, ma'am.
Okay, so thank you.